Welcome to Metrology and Instrumentation, ETS 4502. This lecture would be covering the basic concepts of metrology and instrumentation. The learning objectives, there are 4 learning objectives that are presented to you here. My intention is to introduce to you a basic terminology of metrology, introduce to you some general arrangements of experimental systems, discuss standards and calibration and basic aspects of experimental planning. Again, we try to concentrate on the basics for this particular presentation. The contents of today's presentation is provided to you here. As you can see, we're going to cover quite a bit of material. We are going to concentrate less on the system response. That would be, we leave that to future lectures, and also some of the electrical terminology, electrical engineering terminology that is used in metrology and instrumentation. We would also cover those later when we talk about sensing using different electrical devices. So we try to concentrate more on providing you with the basic terminology first. There are some terminology that are extremely important in engineering, especially in metrology and instrumentation. Those terms, some of which are most important, are provided to you here. It is very important for you to learn and know the meaning of each term that is presented to you here. The first thing is readability, and this may be different than what you've known already. It indicates the closeness with which the scale of the instrument may be read. So that's very important to realize. The second thing is least count. That's the smallest difference between two indications that can be detected on the instrument scale. Again, later on, we provide you with more examples, and these terms there, they would be applied. Sensitivity, and this is the ratio of the linear movement of a pointer on an analog instrument to the change in the measured variable causing this motion. Remember, this is for analog instruments. For digital instruments, it is different. In engineering, we use the term hysteresis or hysteresis. Again, depending on the accent and the way it's being pronounced, these words are not commonly used in English language. They are common among engineers in the field, especially in the field of metrology and instrumentation. For example, when we design a system of a structure, let's say a beam or any kind of a structure, and we take it to the laboratory, we want to test it, we use the hysteretic loop. That's the loading, unloading, loading, unloading cycle for a dynamic load. Now, in metrology, that term is a little bit different. It's a difference in reading depending on whether the value of the measured quantity is approaching from above or below. So if you are applying this to the loading cycle, it's the value approaching from below, and when we are unloading, we are approaching the certain point. We may be approaching certain point from the above, not the below. So this is the difference in reading, depending on whether we approach it from above or below. Is called hysteresis. Then accuracy, you've probably heard that term in metrology. It's somewhat different. Indicates the deviation of the reading from a known input. So when we have a known input, and if there are any if there is no deviation from the reading from a known input, the accuracy we say is 100% accurate. If there is a difference between, then the accuracy won't be 100%. There will be some kind of a deviation. Precision, ability to reproduce a certain reading with a given accuracy, may be somewhat different than 100% accuracy. If we produce something, even though the accuracy of the original reading may not be 100%, if we have the ability to reproduce that value with a given accuracy, then we say that it is precise and precision was met. So we use these terms. The calibration, a term used to double check the accuracy of a known reading or a device. We routinely calibrate our devices against a known quantity to make sure they are as accurate as possible. So the calibration itself, it has different meanings, but the term calibration can also be defined as double checking your work to eliminate errors that may have been overlooked. Again, this is the, in simple terms, this could also be used calibrating equipment, and that is to check them against the known values, make sure that the measurements are correct and the device is working properly. Calibration procedures involve a comparison of the particular instrument with either a primary standard, something that we have it as standard, or a secondary standard with a higher accuracy than the instrument to be calibrated, or a known input source. Again, in your electrical engineering courses, you would deal with calibration more often, but here we also talk about calibration. It's important to know what calibration means within the context of our discussion. So what calibration does, it establishes the accuracy of an instrument. It actually makes sure the instrument works properly. Now, there are also standards that we commonly refer to in metrology and instrumentation. What are they? Again, they are some values that we use in engineering for uniformity and consistency, and make sure that we compare apples with apples, oranges with oranges. Again, those are in simple terms. We are going to cover those more in-depth later. So some of the most commonly used standards units consist of inches, centimeters, again, length, weight, time, temperature. Now, some of these may be quantities, not really the units, but again, I bundle them together now for the purpose. So make sure you understand the inches and centimeters. They are units of measuring length, and in different systems. We're going to cover those later. We're going to concentrate on metric systems, and we're going to concentrate on U.S. customary systems and how we can convert the units between the two systems. So don't get worked out here when I talk about inches, centimeters, length, weight. Those are certain standards and that are provided to, again, make sure we compare same quantities as to incorrectly compare the quantities that are not the same. So in this case, some examples of the units are provided here. 1 meter is 39.37 inches, 1 inch is 2.54 centimeter, and so on. So it is very important to understand the difference between dimensions and units. I've seen people, they make that mistake too often to get confused between dimensions and units. They're different. Dimensions, a dimension is a physical variable used to specify a behavior of a particular system, or to pretty much provides with an important aspect of a system. An example could be, let's say, length. That's a dimension. And then in order to measure that, we would use precise measurement, and for that we would use units. So a length could be, for example, a length of an object, a ruler. It could be 1 meter, or it could be, let's say, 3 feet, 1 foot, and so on. The same thing with mass, force, the temperature, and time that's shown here as tau to differentiate between that time and the temperature, which is shown as T. So L, M, F, T, and tau, they are dimensions, but there are units to measure those dimensions. For example, temperature, T is a dimension, but we measure temperature either, two examples of the units that we use to measure temperature, degrees Celsius and degree Fahrenheit. So let's talk a little bit about the generalized measurement systems. Most measurement systems, again, most, not all, this is the more general category. Most measurement systems, they may be divided into 3 parts, and don't get stuck too much on the stages here. At this stage, we need to get the overall picture. You would need to conceptually understand what a detector transducer stage would do. So a detector transducer stage detects the physical variable and somehow performs a transformation. That could be either a mechanical or an electrical transformation. And what it does is it is going to convert the signal that was detected into a more usable form. If I want to explain this, discuss this more and elaborate on it, a transducer is a device that transforms one physical effect into another. Again, these are mostly electrical because they're much easier to store and much easier to measure. And the signal itself could be analog, it could be digital. You're not going to get too much into that digital and analog. Those would be covered in your electrical courses, but it's important to realize that one of the most important parts of a measurement system is a detector transducer stage. In most measurement systems, there's also some kind of an intermediate stage, and that stage would actually modifies the direct signal by amplification, filtering the signal, or other means so that a desirable output is available. In other words, we try to clean up the signal from noise and other problems that may be associated with a signal. A final or terminating stage acts to indicate, record, and control the variable. And that's the final stage of the cleanup. Actually, we put that on display, and again, the output may be displayed as digital or analog. So here's a diagram that perhaps clarify the what I just described here. Again, there's a physical variable to be measured here, and we get an input signal. We would go through the detector transducer stage, and the signal would be again extracted. It's going to be a transduced signal. It's going to go into an intermediate stage, and from there it is going to again modify the signal. It's going to go into a controller, indicator, recorder. Now there is a feedback control here. Again, the signal would be taken here as a feedback signal for the control. It's going to go back to the physical variable again to be measured. In the process, at the intermediate process, there must be some kind of an external power to be able to perform that kind of an intermediate stage. There's also calibration signal source, which it represent a known value of physical variable. So if the value is way off, the errors would be detected at that time. So it's very important to know how we actually deal with measuring a physical variable. That's the schematics. It provides you with an overall picture. An example is a Borden tube. This is a device used to detect the pressure, and this one is not. This one is gauged. There's a pointer and dial, and that's involved here. A portion of it is shown here. Imagine this pointer and dialer continues all around this device up to a certain point. Again, we took that off because I wanted to show you what's going on with the device itself, and to demonstrate the different stages that I was just described to you. So there would be a pressure source, some kind of a hose would be connected, or it may not be a hose. It could be some kind of intermediate place that the pressure source could be connected to this Borden tube, to this device. The device is the design itself is really not that complicated. It has a sector and pinion. This is the sector, and the pinion is provided here. And there's a hairspring again to make sure the pointer itself goes back to its original stage when the pressure is off. The Borden tube itself, it has an oval cross section. The oval cross section right up here, that's the detector transducer stage. We take the pressure from here. It's going to go through the detector transducer stage. It's going to pretty much, as we increase the pressure, the tube is going to start moving in that particular direction. You see there's a slot provider here to be able to accommodate for that, and the slot that's provided here, it helps with the sector to move. The sector is moving against, turning a small little wheel here, and that would be connected to the pointer and dial to indicate the pressure. So as the pressure increases here, and this dial start to move clockwise, show the increase, measuring the pressure, and actually show the increase in the pressure. It's important to realize the detector in transducer stage would be performed here at this stage, as the pressure is increased in this oval cross-sectional tube, and that would in turn affect the sector, and the sector would affect the pinion, and so on, and then that's how really it works. Let me also talk a little bit about system responses. There are three kinds of main system responses, three categories. And one is the linear frequency response, the other one is linear amplitude response, and the other one is overdriven response. So what it really means in simple terms is, if we want to have a good response for a system, we must treat all frequencies the same within the range of application. Again, we do that because we want to make sure that the amplitude of output to input, the ratio of output to input amplitude, remains the same over the frequency range desired. The linear amplitude response is the ratio of output to input amplitude. Again, we try to keep that. That should remain constant over some specified range of input amplitude. If the linear range is exceeded, as in a voltage amplifier, where too high an input voltage is used, that is called overdriven. Again, these are three types of system responses. Don't worry too much about their definition, and try to mostly understand what's going on. Again, in order for the system to have a good response, it must treat all frequencies the same within the range of application, so the ratio of output to input amplitude remains the same over the frequency range desired. That's the linear frequency response. And the linear amplitude, it's kind of similar. However, the ratio of output to input amplitude should remain constant over that range, over a specified range of input amplitude. Where do we get those ranges? Again, that's more complicated. I'm not going to get into those now. Later, as we go through the course and you do more reading of the book, we can discuss those in more detail. So it is very possible for us, the way I just defined it previously, distortion, the variation of a signal from its true form. So if there's any kind of a distortion, that means we are going to have some kind of a variation. So the device is not going to provide us with the true signal or the real signal. It's going to be some kind of a variation depending on the system. So this distortion, the sources of the distortion, it may result from either a poor frequency response or a poor phase shift response. These are more for dynamic systems, applied more to a dynamic system. So again, depending on what kind of a signal we have, what kind of device we have, in electronic devices we use various circuits to reduce the distortion to a very small value. Usually there are some distortions, but they could be very small, that it could be negligible. For pure electrical measurements, distortion is easily controlled either by analog or digital means. It is also important to realize that we need to have impedance matching. In many cases, it is necessary to connect various items of electrical equipment in order to perform the overall measurement objective. The impedance matching problems, they are usually encountered in electrical systems, but they can also be encountered in mechanical systems as well. So it's important to make sure that we don't run into impedance matching problems in which it's going to affect our measure. So let's move on to a more important part of today's discussion, which is experiment planning. So how do we actually go about planning an experiment, and how we go about planning a successful experiment, not just an experiment, but a successful experiment. So there are certain rules and guidelines that we need to follow. First, we need to ask certain questions from ourselves. It's the what and why. What am I looking for? What is it that we try to achieve? And what am I measuring this? Why? And then, does the measurement really answer any of the questions? That's very important. Many times we make the measurements blindly, and the measurement may or may not answer any questions. So it's very important to realize that we can't just measure something. We would measure it because we try to find out the answer to some questions. And then, what is the meaning of that measurement? So we have a bunch of data in certain units. What does that really tell us? So again, these are the questions that could be very complicated to answer, and they could be much simpler to answer depending on the experimental work that is involved. So for that, when we after we address these questions and what we try to do, then we would move on to the experiment planning stages. Again, these are some of the rules and guidelines that would help us plan an experiment successfully or for planning for a successful experiment. So, question number 1. What are the variables? What are the primary variables? Not just all the variables. There could be too many. But what are the primary variables? And which one of those should be investigated? What control must be exerted on the experiment and make sure the parameters are within a range and within reach, and we can't just measure any type of a variable for any reason. We want to make sure we are within a certain range that would control the experiment itself. What ranges of the primary variables will be necessary to describe the phenomena under study? That's also important. What are we studying, and what will be the range of the primary variables that are involved? Again, these questions are very important, and they can help us think and rethink about the experiment. So let's take a look at this. After we, this is a diagram that would clarify some of the questions that I just discussed. First, we need to establish a need for the experiment. As I'm going through these, I'm going to put a red check mark by it to clarify that we already covered. So it is very well possible that the experiment that we are trying to establish the need for has already been done. In that case, we need to establish the modification. Why is it need to be done again, and what do we modify? It could be simply the inaccuracy of the original experiment that forces to modify and look for a new modified experiment. So that's also could be the reason. So let's say we establish the need for an experiment. Well, obviously we need the financial resources for that. People don't work for free, so there's some kind of a time and financial resources that need to be identified here. Obviously, with any resources there would be limitations. It's very important to realize. So if it is not feasible, then what happens? Well, you need to somehow reduce the scale of the experiment if we can, or in some cases the experiment cannot be done because not every experiment could be simplified, again depending on the type and the scope of what we try to achieve here. Those of you that have had experience with metrology and using different instruments and try to plan for an experiment, you would know what I'm talking about. That's why some organizations, they sometimes abandon the experiment because it's just not feasible. So let's say that we establish the need for the experiment and we establish the time and the financial limitations. We have the resources, then we move on to the next stage. So when we're done here, and then we move on to the next stage, which is estimate scope or accompanying analytical work. What kind of analytical work, analytical modeling, and analytical analysis, what kind of analysis would go into this experiment? And that's also important to realize. Also, analytical tools are used sometimes to verify the experiment. That's also noteworthy. So there goes the review of the literature after we estimate the scope of accompanying analytical work. This means we need to go back here and we need to review the literature. Probably heard of that, the literature review. That's where it comes into picture. Many projects that you guys would submit, the professor would ask you to do the literature work. For senior design project, this is extremely important. We ask you to do a thorough literature search for your senior design project for this particular reason, for you to know what's out there and carefully review the previous work, and in order to pretty much after reviewing that work, you'll be able to modify the need for the experiment, or pretty much provide a solid argument for the need of the experiment. So after we're done with the careful review of the previous work, we need to establish general feasibility within original budget and time limitation. Again, there are feedbacks provided here, like a loop here. For example, from this particular part here, we get two types of feedback. One is if it's not feasible, we need to go back to the modification of the budget, that's the financial limitation, and time pretty much goes back to green money. And as you can see, this loop would be continuous throughout this particular diagram. So let's say we have established the need solidly, and we can begin preliminary analytical work in order to do what? Well, the preliminary analytical work is going to help us with a very important aspect of the experiment. What variables are we looking for? What kind of range and accuracies are required? And then from there, we can determine what kind of instruments are required. Remember, so far I have not talked about the required instrument for a particular experiment. We were talking about the setup. And then now, what kind of instrument we can specify, what kind of instrument we need to buy. Again, originally we did some preliminary work in order to justify the budget for our instrument, but now we have a much more understanding of what kind of instrument do we need with, we can budget it more accurately. I've done this in almost every project that I've been involved with. So some of these diagrams, some portion of the diagram is more important, and some of them they are less important depending on the experiment itself, but they're all part of the overall planning for the experiment. So we modify the instrument in accordance with the budget limitation, and then we get we purchase the instruments, and then for that, after purchasing the instrument, then we would use those instrument in later stages of our experiment. So if there are needs for construction of special equipment, we need to do those at this stage. We arrange for design and construction of special equipment. Not every equipment could be used in a different experiment. It is very well possible that if you're dealing with huge, for example, structural pieces, it is possible that if you have a 30 feet beam, obviously for that we need to go back and construct a special equipment. We need to have a construction, in some cases we need to build a new facility to be able to accommodate that. Or if it's supposed to be performed outdoors, we need to be aware of the limitations. We would, for example, load this beam to failure. We want to make sure if there are bolts involved in the connections, they're going to snap off. It's going to really cause problems. I can give you one experiment I was involved. It was in downtown Los Angeles. So you had this experimental facility. We were testing a beam to column connection, and we loaded to the failure. It was a new post-Northridge earthquake connections. We loaded to failure. The minute that the bolt actually failed and it just sheared off, it just made this huge loud noise that it made the alarm of many cars in the adjacent parking lot to go off. So they were complaining to the city right away that this experiment and causes too much noise. So we had to go back and modify our experiments, make sure that the noise doesn't disturb. Although this was an industrial facility, we want to make sure that when we come back and modify our experiments, so when the bolt snapped off, sheared off, the experiment was in such a way that we had to push this to failure, push the prototype to failure, and the noise would have been a concern. That was just an example. Anyways, I have many other examples that I can discuss with you later. So from that, if there's any need for special equipment, that needs to be constructed right there. Again, parallel to the experimental work, we proceed with the analytical work. We again go through this feedback loop. We compare the preliminary data with theories available. We're going to go back and we check to see if we need to modify in the experiment and or analysis. We need to do the same thing. We need to do it right here, and the feedback is going to go back to the arrange for a design and construction of special equipment. It's always a good idea to collect a few preliminary data points. Don't go through the experiment fully, gather this huge amount of data, and that may or may not be useful. Again, these are like checkpoints for us, help us to collect the data in a much more efficient and useful way. Then with any data, there is uncertainty associated with that. We would cover that later in this course when we get into that portion of the course. And so, again, each stage is very important. The information that we gather at each stage is used to as a feedback to go back to some other stages to constantly correct and modify the experiment if necessary. So we collect running the experiment with the available instruments that we already planned for, and we collect the bulk of data. Again, we continuously perform the analysis in parallel, and we go back and we modify it if necessary. So after gathering all that data, then we need to go back and sit down with the experiment team and match theories with experiment, see if there are correlations, how we can correlate the data. We create new theories to explain data, etc. And then hopefully we should be able to discuss and publish results of experiments. This is the type of experiments that is performed at institutions of higher education, also the type of work that is performed in the industry. The process may be somewhat different, but the results, they should all compared with the theory, find a correlation, create new theories, and to explain data, etc. Again, this is the heavy-duty experiment, and it's not really what I call the Mickey Mouse experiment. This is the heavy-duty. Nothing wrong with Mickey Mouse, but you know what I'm talking about. It's not a cartoon experiment. It's a real world experiment that results in a scientific advancement, and it results to a better life for all of us. So in summary, what we have discussed today and what you need to know is we need to understand the engineering terminology, since engineering and sciences we use, in engineering and sciences we use precise words that has precise meanings. And the best example is stress, S-T-R-E-S-S. What it means in engineering and strength of material. Every time we deal with material, it's very different than stress. And when we deal with the field of psychology, or we use that term loosely in our day-to-day life, you know, if a person says I'm under stress, that is very different than if we put a rod or a piece of structure under stress, or a cable under stress. Very different meaning. So we need to make sure we understand the engineering terminology. Also, we talk about calibrating any instrument. For example, if a person weighs 180 pounds on a scale, and you may your weight would be closer to 160, then there would be 20 pounds or 5 pounds or what have you weight that could be added, or the best thing is to calibrate the scale. Also, standards are very important in engineering and sciences. Dimensions and units are different. One is to describe a quantity, or could be temperature, length, what have you. The other one is to actually measure it. Units come into picture. When measuring the length of a table, length is the dimension. It may be 36 inches. If we just say 36 long, 36 watt long. That's why we in the engineering community, we are so meticulous about units. And if you don't express units, especially in this class, points would be taken off. You would lose credit. This is a metrology and instrumentation. If you got away with that in some of your other classes, in this particular class, you cannot get away with that. It's very important for you to express the appropriate units. No excuse not to, especially in this class. The generalized measurement systems is used to transfer data picked up from one particular device to another. Again, the different measurement systems that we are going to deal with later. And very important to realize that we need to constantly ask ourselves questions every time we try to first justify an experiment and a plan for an experiment. We need to know with good accuracy where is it that we are going and what is it that we are looking for. We can't just start playing around with devices hoping that we can get some kind of a measurement out of them. We need to define all the variables. What is it that we are looking for, and what do we do with the data after we collect it, and where does those data would lead us? What do we try to do? It's very important to plan for that in the minds first, then move it into the experiment stage. That brings me to the end of slides for today's discussion. If you have any questions, please feel free to send your questions and comments to me via the course website. Thank you for your attention.